Okay, folks. Here's the last section from last part of the section of 2.1, and this is going to be arc length and area of a sector of a circle. Okay, so arc length and area of a sector of a circle. Okay, so here we have a circle. Okay, and on this circle we have a central angle C, and this right here from B to A is our arc length. This is our arc length, S. So this length right here would be the arc length, S. Okay? Now this angle here, this would be our angle theta, the angle that's subtended by the arc length, and this would be our radius. So you've got the angle subtended by the arc length S with radius R, just like we studied in our last section between radians and degrees, okay? And in chapter 1. Now, when we talk about the area of a sector, then this right here, this part right here, would be the sector of our circle. This would be our sector, okay? So when we start talking about the area of that sector, that's what we're looking for. We're looking for the slice of pie, so to speak, okay? So in the first part of this section, we learned that we could take an angle theta, and if we divide the arc length by the radius, we could get it in radian form, okay? So to find arc length, a formula for arc length, all we have to do here is solve for S. So S equals R theta when theta is in radians. That S equals R theta would be an easy formula for the arc length. Now, what if theta was in degrees? Now, we take our same formula and multiply it times pi over 180. Now, that's our conversion, remember. If it's in degree, if we start out in degrees, we have to convert it to radians. So we have to multiply our answer, since we're starting in degrees, by pi over 180 in order to be able to convert it to radians. This was our radian to degree, degree to radian conversion factor that we talked about early in the section. Okay, so for instance, let's look at an example. We have our example here, and it says, let me get this set, it says in a circle with radius 6 feet and the arc length is subtended, by a central angle of 1.7 radians. So it's subtended by a central angle of 1.7 radians. Okay? Now, what would be the arc length? So we have the radius, we have the angle. Okay, this would be theta, this would be the radius, of course. Now, since this is in radians, we're going to use the arc length formula, r theta. So very easily we can say 6.00 times 1.7. And this would give us our arc length. Okay, this would give us our arc length. So if we did that, get your trusty calculator out, one of the few times you'll hear me say that. And this would be 10.2 10.2. Okay. Don't know what happened there, but this would be 10.2. Now, 10.2 what? Well, we're talking about a length. This is arc length. What length do we have here? Feet. So this is 10.2 feet would be our arc length. Now, what if instead of 1.7 radians, what if we did 40 degrees? Okay, 40 degrees. Well, remember, if we do 40 degrees, we have to use the degrees formula, which is our radian formula here, just multiplied by our conversion factor. Multiplied by the conversion factor. So, same mode of thought here. Pi over 180 times, well, what's our R? Our R is 6.00, excuse me here, 6.00 times our theta, which in this case, theta here is 40 degrees. So times 40. Okay. I'm getting a rush. This thing kind of looks a little sloppy. Alright, so multiply it out. And so again, take your trusty calculator. Make sure we have 6 times 40 times pi. Remember to use your pi button, divided by 180. Now, let's suppose that, let's just say we want to round this to 3 decimal places. So if we round this to 3 decimal places, right here, we would have 4. We would have 4.189. 4.189 if we rounded to 3 decimal places. So this would be our formula, how to use the formula for arc length. Now, what about the area of a sector of a circle? Well, as we discussed earlier, if I have my circle, and if I have my circle here, and we have a center of the circle, and we have our edges, then of course this right here would be our arc length, right? This would be our radius. This here would be our theta, as we discussed earlier. Forgive me for my circle, please. And this right here would be our area of the sector of the circle that we're trying to find. Okay, so at this point, what do we have? Well, the formula for the area of a circle with radius r and the central angle theta can be used by solving the following proportion. So if we have the area over pi r squared. So think about what we're doing here. We're trying to find the area of the sector, so we're going to proportionalize it to the area of a circle, which is pi r squared. Well, that's equal to theta, which is our angle, okay, over the angle of our, or over the circumference of our circle, which here would be 2 pi in radians. So if you were to solve this, this would be a times 2 pi. What we're going to do is let's just solve this for a. A times 2 pi equals theta times pi r squared. Divide by 2 pi. And so the pi's would cancel here. And I would get 1/2 theta r squared. Now this is in where theta is in radians. Theta is in radians, okay? Now your next thought should be, well, Mr. Francis, what if theta is in degrees? What if theta is in degrees? Well, we have to change it up a bit, okay? We can take our formula, A equals 1/2 theta r squared. Now, it's in radians at this point. So to convert it back to degrees, we need to use our pi over 180. Now, you got to think, at this point right here, theta would be in degrees, and we're converting it to radians. So notice what we're really doing here. Between whether it's arc length or whether it's area of a sector, when theta is in degrees, notice how we have our conversion factor flipped. Pi is on top. So we are actually changing this back to radians. Every time the theta is in degrees, with arc length and with sector, we are changing it back to radians. I don't know if you picked up on that, but that's what we're doing. So if we simplify this a little bit, 1/2 times pi over 180 is pi over 360 theta r squared when theta is in degrees. So here are our two area of a sector formulas. Okay. Now remember, don't start stressing on me now. You will get formula sheets. I will provide them for you for the exam. There should already be one online in Canvas. Just look around, and I'll post it again a little closer to exam time so you can familiarize yourself with them. And I'll give you one of these formulas. I'll probably give you the radian form and expect you to get the degree form based on that. Okay, so keep that in mind as you are preparing for your exams. So let's look at an example. So we have an example here, and here's what our example says. Our example says that in a circle that has radius 3 meters, find the area to 3 sig figs, 3 significant digits, okay, 3 sig figs, okay, of a sector. Find the area of the sector, okay, when the central angle equals, so for our first problem, we're going to let the central angle equal 0.4732 radians. Okay, so what's the area formula of a sector when it comes to radians? 1/2 r squared theta. Okay, so this should be very easy. This is just a plug and chug. R is going to be 3 here, and theta is 0.4732. 0.4732. I typed R. That should really be a squared. There we go. 1/2 times 3 squared times 0.4732. Now, this is going to give you approximately 2.13. Now, we're wanting 3 significant digits, so we're going to leave it at 2.13. 3 significant digits. But this is an area, so obviously area has to be in some kind of length, okay? So we know we have meters, but remember, area is never just meters. Area is always square something, square feet, square meters. So this is meters squared. And notice we are squaring the meters right here. That's we square the units as well. So there's our area of the sector when we have our degrees in our angle in radians. Well, what about degrees? Okay, what about degrees? Well, what's our area formula? And remember, that's pi over 360 times r squared theta. Okay, well, so that's pi over 360 times r squared. Well, r is still 3, whether it's in radians or degrees, r is still 3. Now, our theta here is in degrees, so it's going to be 25. And remember what this first part, the pi over 180 part of this, pi over 360, the pi over 180 part of it is changing our degrees to radians, essentially. Okay, so rounding this to 3 significant digits, we get 1.96 square meters. And that would be the area of a circle. Now, folks, we worked a good many problems through this section. And you got to know formulas, you got to be able to plug in. But when you get to some of these, you need to take your time when you get to some of these application problems. Because remember, with application, the key to it is applying these formulas to a real life situation. So here's what I would do to better help you with application problems. When you get to an application, find out what you're looking for. So if it's area of a sector, what do I need? Well, I need to know the radius, I need to know theta, whatever the angle is, and I need to know whether I'm using the degree or radian formula. If it's in degrees, I'm using the degree formula. If it's in radians, I'm using the radians formula. I know that seems kind of obvious, but you'd be surprised. But find out what you have, what you're looking for, what you have in the problem, and then apply it to what formula you're going to use. Okay? You've got to be able to identify the key units of each formula in these problems. If you can circle, I would just go through the problem, circling the units and circling what I'm looking for, and then find out which formula relates those. That's what you're trying to do when you are looking at an application style problem. Let me know if you have any questions. If there's an application style problem that everybody's having questions with, like the one last week, I'll post a video on it. So let me know if you have any questions. Have a great day.